Okay, lecture number 10 here for chapter 18. We are going to put together all this information we have been talking about into one cardiac cycle. Go away. And yes, I'm working at home, and one of my dachshunds is starting to whine, so they could start barking at any minute. Just be wary. That could happen. All right, one cardiac cycle. Here we go. All right, so what do we mean by a cardiac cycle? So a cardiac cycle literally refers to all the events associated with blood flow through the heart during one complete heartbeat. So we're going to go through this whole story and see how these things are coordinated. A couple of new terms, though, that we need to know. Systole refers to contraction of the myocardium. Diastole refers to relaxation, and you've probably, those terms might be familiar to you but you've probably heard them before as systolic and diastolic with regard to blood pressure. Systolic blood pressure and diastolic blood pressure. And now that's because your blood pressure changes are controlled by heartbeat. As the heart contracts, it squirts more blood up into the blood vessels, and that's when you achieve your highest blood pressure. As the heart relaxes, it's not squirting additional blood up into your blood vessels, and so your blood pressure will gradually fall with each heartbeat. That's your diastolic blood pressure. At that point, your highest blood pressure is called your systolic blood pressure. All right, but with regard to the heart, systole refers to contraction of the walls of the heart. Diastole is relaxation. All right, one cardiac cycle takes 0.8 seconds in an average individual, and that's assuming a heart rate of 75 beats per minute. As you guys know, that varies from individual to individual. I mean, it can be super low in endurance athletes and triathletes and so forth who do a lot of endurance exercise all the time. Their resting heart rates can, be below 40 beats per minute or even lower in some cases. But we're going to use this 75 beats per minute as an average, and again, that's 0.8 seconds per cardiac cycle. And what's going on during each cardiac cycle? It takes about 0.1 seconds of the cycle for atrial systole to take place. So that's 1/10 of a second for the atria to contract. And the atria don't have to contract all that forcefully because they've just got to wring out some of the extra blood in there and make sure that it moves down into the ventricles. But they're getting help from gravity for blood flow between the atria and the ventricles. Ventricular systole lasts for about 0.3 seconds. So that's when the left and the right ventricles contract together. And so the grand total there is 0.4 seconds. And the other 0.4 seconds, you're going to have a relaxation taking place before you start the whole thing over again. All right. Something else we need to talk about before we start walking through the whole cardiac cycle, one round of the cardiac cycle, are the heart sounds that take place. So when you hook up somebody to a stethoscope and you're listening to their heartbeat, you guys know. Hang on, my little pen thing here has disconnected from my computer screen, so I'm not able to draw. All right. Sorry about that. We had a little glitch. Okay. Heart sound. So you guys know if you were listening to somebody's heartbeat with a stethoscope, you hear boom, 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 and that's sometimes referred to as the lub-dub sound. And what's actually causing that sound? It's actually, what you're hearing is the closing of the heart valves, believe it or not. So this first sound, lub, occurs as the AV valves close, your tricuspid and your bicuspid valves, because they're going to close as the ventricles start to contract so that you don't have that backwards flow of blood from the ventricles into the atria. The second sound occurs as the walls of the ventricles are relaxing and the blood starts to flow backwards due to the reduced pressure in the aorta and the pulmonary trunk, and it gets captured in those semilunar valves like we talked about earlier and they close, your aortic and your pulmonic semilunar valves. So that's the duck sound that you're hearing when that occurs. Abnormal heart sounds that can be heard with a stethoscope are referred to as heart murmurs. And when those occur, sometimes you have a valve that is not closing completely off, and you'll hear abnormal sounds because you'll have some blood flow from one location to another when it's not supposed to be occurring. Okay, and if they need, if a nurse or a physician needs to check out heart sounds in more detail, this is a diagram from your textbook which is showing where you can actually place the stethoscope on the chest to more closely hear particular valves. So they're showing you if you place the stethoscope there, you're really going to be primarily hearing what's going on with the aortic valve. So if there are any abnormalities suspected there, you could place the stethoscope at that location. You would put it over here to listen more closely to the tricuspid valve, over here for the mitral valve, and over here the sounds that you would hear would give you a better sound information from the pulmonary semilunar valve. And notice too, if you look there on the information on that slide, they're mentioning intercostal spaces. Remember, costal refers to the ribs, so you're sticking the stethoscope into the softer spaces that you can feel on the chest between the ribs. All right, so let's start talking about what's going on with one cardiac cycle. We're going to walk through the whole thing. So you have to pick a beginning point, and a cardiac cycle is considered to begin as the heart is in diastole. So it's in a relaxed state. So that means both the atria and the ventricles are relaxed. When that's occurring, your AV valves are open at that time, this one and this one. And so what's occurring, you've got blood entering the right atrium from your inferior vena cava, your superior vena cava, and also the coronary sinus. Don't forget about that. You have blood entering the left atrium over here. It's coming back through the pulmonary veins, returning from the left and the right lungs. And when those AV valves are open, due to gravity, blood is just passively flowing. That means it's not being forced. It's just passively flowing down into the left and the right ventricle from the two atria. So that's what's happening when your heart is completely relaxed, this passive filling. And the ventricles, about 80% of the filling that takes place in between heartbeats occurs during this time. 80% of that is passive. All right, then the next event during the cardiac cycle, at this point ventricular filling finishes up. It completes. And in order for that to happen, we have to start with the SA node is going to depolarize. If they're showing you there, that impulse is going to spread across the walls of the atria. Those electrical changes, those action potentials lead to contraction of the atria. That's called atrial systole. And what that's going to do is residual blood, that might be over here in the auricles. Remember those little ear-like flaps you've got on the atria? That helps squeeze any residual blood down into the ventricles. So that's why we actually have to contract those atria. Okay, that completes the ventricular filling process, and at that point we have what's called an end diastolic volume, or EDV, and on average that's 120 milliliters. Okay, that value of 120 milliliters is an average, and it means 120 milliliters roughly in the right ventricle over here, and about 120 milliliters over here in the left ventricle as well. 120 is about average for the left ventricle, and from what I understand, the range is more like 100 to 160 over in the right ventricle. So that's where we are at this point with our one heartbeat that we're going through. All right, the next thing that's going to have to occur is ventricular systole. So the atria, which don't contract all that strongly, but they do contract before the ventricles. So what has to happen next is that depolarization wave that started over here at the SA node, and by now it is spread over here to the AV node. It passes through the AV bundle into the bundle branches, and then outward through the Purkinje fibers. And that's going to lead to the action potential, the electrical change spreading all the way across the ventricles of the heart. That's going to trigger all of the cardiac muscle fibers within the walls of the ventricles to contract. So you're going to have ventricular systole. Also, what's happening right now, remember those papillary muscles also contract. They pull on the chordae tendineae, and those shut down those AV valves. So you'll hear that lub sound on the stethoscope. Where would we be right now on the ECG tracing? Okay, if we think about that, a typical ECG tracing, P wave, QRS, then you got your T wave over here. So where are we? You know, earlier we had our P wave occurred as the atrial walls depolarized. Here we're talking about the ventricular walls depolarizing. So at this stage, we've had this occur, and then the ventricular walls have contracted, ventricular systole. Okay, now what has to happen? Okay, so ventricular systole has occurred. We now need to relax the ventricles. So in order for that to happen, your ventricles have to repolarize. So where would we be on our ECG tracing? We've done our QRS because that's what leads to the ventricles depolarizing. So now we're going to have our T wave over here, which is going to be the electrical tracing that would result as these ventricles wind up repolarizing. As this occurs, your ventricles relax, so they enter diastole. We're entering ventricular diastole. So you've got blood up here in the aorta and the pulmonary trunk. Here's your aorta right in here. And remember, you got blood up in here as the wall of the left ventricle is relaxing. Gravity starts pulling the blood back this way. There's no pressure, there's no force that's squeezing that blood upward. And so that's going to get caught in those semilunar valve cusps. And same thing's going to happen with the pulmonary trunk that's connected to the right atrium. And you're going to hear that duck sound as the valves close, as that blood backflows. Okay, so what's going on right now, the ventricles have contracted. You've squeezed all the blood out that you're going to squeeze out of the ventricles. And at that point, you have what's known as the ESV, or the end systolic volume, is 50 milliliters. And again, this number is on average referring to the left ventricle over here. Should be similar for the right ventricle as well. So if you guys remember, we after the ventricles were filled, we had an EDV of about 120 end diastolic volume. And now the ventricles have contracted, they've squeezed blood out and up into the pulmonary trunk and the aorta. This is what you have left, 50 milliliters. So how much blood did we actually squeeze out of the ventricle with this ventricular contraction? 120. Before we started the contraction, you have 50 milliliters left. So 70 milliliters is the amount of blood that got shoved out of the left ventricle and up into the aorta with each heartbeat. And that's on average. That's going to vary from person to person, which we'll be talking about soon. Okay, so, one thing I forgot to mention, me back up over here for a minute. There is a phase while the ventricles are in the process of relaxation, that's called isovolumetric relaxation. And iso, that prefix means same, you know, like isotonic, referring to solute concentrations in your body fluids being the same inside cells versus outside. So this means same volume relaxation. What this means is there's a period of time while the ventricles are relaxing during which your blood volume stays at about 50 milliliters in here. And the reason for that is because while they're in the process of relaxing, you haven't relaxed them yet enough to open up these AV valve flaps. Once those open up, then blood's going to start to passively fill the ventricles again. But there's a brief period of time during which you still have enough pressure within the walls of the ventricles to keep those, and those papillary muscles to keep those AV valve flaps closed. So there's a little bit of time in there when the volume in the ventricle stays the same. That's called isovolumetric relaxation. Then eventually the pressure reduces enough in the walls of the ventricles to allow those valve flaps to open, and you know, you've had blood returning over here into the right atrium and over here into the left atrium, and that starts flowing again down into the ventricles. More technically, what does it take for these AV valves to reopen? It's when your atrial pressure exceeds the ventricular pressure. So as the ventricles relax enough so that you've got more pressure up in the atria due to the blood that has flowed back in there, that's going to cause those valve flaps to open, and you'll start your passive ventricular filling all over again. So that's the story that you go through with one round of the cardiac cycle, and you guys should know that story. I mean, you should be able to write that story out step by step. One thing leads to the next, leads to the next. If you understand heart function, it's not hard to remember that, but you need to know that story. It'll be very difficult for you to kind of critically think through heart function questions if you don't understand that story. This is a pretty good diagram from your textbook. It looks kind of scary when you're first looking at it. And the best thing to do is to take a look at this diagram either here or in your textbook and see if you can follow along what's going on. What they're trying to, this is representing one cardiac cycle, this graph, and they're showing you what's happening during this 0.8 seconds of one cardiac cycle. And they're trying to show you, what's going on simultaneously as this occurs. So up here on the top, they're showing you, here's what happens during one cardiac cycle if you're looking at the ECG. So there's a P wave, a QRS complex, and then there's your T wave over there. Then they're showing you on the same timeline when you would have your particular heart sounds. So there's your love sound there. Notice that that's a little bit right after the QRS complex. That makes sense because the QRS complex is the electrical activity around the ventricles that causes the ventricles to contract. When the ventricles start contracting, the AV valves close and you have that love heart sound. So that's going to be a little bit delayed because the QRS complex has to occur and then the ventricles contract, which leads to the AV valves closing. Same thing with your second heart sound over here. That's going to follow the T wave right in there because the T wave is repolarization of the ventricles. That's going to lead to them relaxing. It's the relaxation of the ventricles that causes blood to start to flow backwards in the aorta and the pulmonary trunk, and that blood gets caught in those semilunar valve cusps, and you have the closure of your semilunar valves. So that's what they're walking you through here with this diagram. In this section, they're showing you the pressure changes that occur, like within the ventricles. Pressure's going up in the atria as the atria contracts. Pressure's going up in the ventricles as the ventricles contract. And kind of neat too, they're showing you, they're measuring this pressure. Pressure is often measured in millimeters of Hg. That stands for mercury. So you know the old-timey pressure gauges, like blood pressure gauges, where you have mercury inside the gauge, like you inflate the blood pressure cuff and you see the mercury rising in the little tube. You know, that movement of the, or displacement of the mercury in those types of gauges can be used to give you a numerical value for pressure. Hg is the chemical symbol for mercury, so that's what that's referring to. So they're showing you on here, like the pink line, those are the pressure changes that occur along this timeline in the atria, or the blue line over here, that's the ventricles. The green line is actually the pressure changes occurring in the aorta itself. So the pressure in the aorta is going to go up when the ventricles, poof, squeeze blood into the aorta. You have that burst of blood that occurs in there, and so that's going to cause a big jump in pressure in the aorta. And then as that blood flows out of the aorta and elsewhere in the body, pressure in the aorta is going to drop back down. So that's the green line that they're showing you there as well. Then the black line down in here, this part of the graph, they're showing you the ventricular volume. So your end diastolic volume after passive filling, after the atria have contracted, goes up on average to about 120. And then as the ventricles contract, which you're seeing there with that big hump, it's going to drop down to about 50. And then you're going to start your passive filling over again as the ventricles relax. So I'm not going to go through a step-by-step explanation of everything on that graph because it would become very difficult to follow. But it is something to take a look at and see if you can understand what's going on in that graph, because it's trying to give you a graphical representation and some numbers on all the things that are going on with one cardiac cycle. All right, so now that we understand what goes on, all these coordinated events that have to take place with one heartbeat, that's going to lead us to a really important topic, and that is cardiac output, sometimes abbreviated as CO. And I do want you guys to keep in mind this value, that's 70 milliliters. We said that's the volume of blood ejected from the left ventricle with each heartbeat, because that's going to come up again as we move on to cardiac output. That volume of oxygenated blood that you're sending out of your left ventricle with each heartbeat is really the most critical thing to the rest of your body. You know, are you sending adequate amounts of oxygenated blood out into your artery so that it can be distributed to all of your tissues that desperately need those nutrients and oxygen gas molecules so that they can function and survive? So that's where we'll move on to with the next video lecture, CO, or cardiac output.